Let's take a look at lesson 11.7, the last lesson for chapter 11 of inferential statistics. We have a bell ringer here to review of hypothesis testing, and then we'll start with our new lesson. So number one here, oops, there it goes. It says for the claim K, use the specified information to calculate the test statistic and determine whether there is enough evidence to reject the null hypothesis. Then make a statement regarding the original claim. And so here's the claim K. It says the claim is that the mean is less than 540. So from there, we could establish that, remember, the null hypothesis always takes the equal sign. That means the mean must be this that has no equal sign, it's just less than. That means the null hypothesis would be that the mean is greater than or equal to 540. The alternative hypothesis is that the mean would be less than 540. And since that is our claim K, I'm going to write here claim. This is the claim. And so this is what we're evaluating here. It says we have a mean less than, let's go over to our calculator here while I talk about this hypothesis testing. It says, so we're testing that the original mean is 540 greater than or equal to 540. We'll go to the alpha here. It needs to be 0.1. Since it's just a less than, according to the rules, let me scroll down here. Since we're looking at the mean just being less than, it's a one-tailed test, and it'll be on the left side. So I'll show you the visual for that in a second. And let's see here. It says the X bar, which is the mean of the sample, is 525. We have a total number of samples that is 50. So to use the normal distribution rather than the t distribution because it's greater than 30. The standard deviation here is 20. And let's see, is that all of it? Alpha, we got all that information in there. Okay, so now let's show you the visual. You can see it's in this critical region because it's shaded there. What I'm going to do is go to the alpha visualizations. Since we're only looking at the one tail, it's the left side because the mean, we're testing the alternative that the mean is less than 540. I'm going to turn the left on the normal distribution on, and I'm going to zoom in here so you can see. So this would be the critical region in here, and this t statistic or the p-value is way over here. This t statistic itself is way in the critical region, and you can see that p-value is so close to 0. And anytime it's less than the alpha, you would reject the null hypothesis. And so that's what we're going to do in this problem. Where is my p-value? Sorry, I'm in the alpha. I'm back in visualizations. Let's come back down here to hypothesis testing, and the p-value it says is, wow, this is basically 7 zeros before 5. So 0.00000000568, so on and so forth. It's an extremely small number. That is definitely less than 0.1. For that reason, we're going to reject the null hypothesis. So we'll reject the null hypothesis, and since we're rejecting this, this looks like it's not rejected. And so we're going to look how we want the claim to not be rejected. Perfect, right there. So the answer is going to be D. A would also be out. This is the part that makes A wrong. All right, now let's take a look at part or number 2. It says Jacob claims he can buy a new MP3 player for less than $50. So the claim is he can buy it for less than 50, not equal to, but less than, which means it has to be an alternative hypothesis, is that the mean is going to be less than $50. With that information, I'm going to write out that the null hypothesis is that the mean is going to be greater than or equal to $50. Again, this is going to be a one-tailed test here because it's just less than, which according to this tail, if it's mean, if the alternative hypothesis has a mean less than K, it's one-tailed, and it'll be a left side test again. So here it says, let's start changing our numbers. The mean of the population is 50. He checks the prices at 15 different websites. Okay, that's the number of samples. So this will be a T distribution we're going to be looking at. And the average price of the MP3 player is $49.25. $49.25. The standard deviation for the samples is 220. So I'll put that on there. Find the p-value, determine whether there's enough evidence to support the claim at alpha being 0.5. So let's go to 0.5. We want this to be one tail, but one thing I need to do is switch my visualization. We're no longer looking at the left tail as a normal because we're less than 30 samples. We're going to use the left tail of a t-distribution. And the degrees of freedom, remember, is 1 less than the sample. So it'd be 15 minus 1, which is 14. So you can see that's the critical region here. Let me kind of zoom in better. There's the critical region. This t statistic is not in the critical region. For that reason, we would not reject. So we would fail to reject the null hypothesis. The claim, which I didn't write that up here, we were claiming this, we would reject the claim. So we would fail to reject, but reject the claim. This is the p-value. The test statistic would be negative 1.32. The p-value is 0.104, which I need to have this updated. Hang on 1 second. And now I have the answers updated. And so we do have the p-value at 10.4. And it says, is there enough evidence to support the claim? So since we're not rejecting, we fail to reject the null. I'm going to point this out. Since we're failing to reject the null, that means we do reject. There is enough evidence to reject the claim. Specifically, let me point at the claim. So we're going to say 0.10 and enough evidence to reject the claim. Oh, and I'm sorry. Enough evidence to support the claim? No, we're not supporting the claim. So we're actually going to reject the claim. So I should be going with C here. All right. Well, 11.7, as you can see in the top corner, we're going to be talking about correlation and linear regression, stuff that you've seen throughout your time in algebra, at least in Dallas Independent School District. You should have seen this. But today we're going to find out, how does the calculator actually work the regression, and can we do it on our calculator here? And the answer is yes. I'm going to go ahead and just refresh that so it's gone. But that's what we're going to look at. If you want to pull up this calculator, scan this QR code, and at the very bottom, near the very bottom, click on your AP Statistics link right there, and then I'll pull up this calculator. All right. So let's talk about linear regression. There's going to be all these different words, but there's only a few of them that I'm really going to spend a lot of time on. First is the correlation coefficient. It's represented by the letter R. It says for n pairs of sample data of the various variables x and y, the correlation coefficient between x and y is given by this. And so really, however many samples you have 1 divided by the samples minus 1 times multiply the sum. This is going to be any particular x value in a sample minus the mean of the x data set divided by the standard deviation of the x data set times whatever the particular element of the y or the second data. And so it's called bivariate because there's 2. The second element or the second data set element minus that second element, second data set's mean divided by its standard deviation, which is a mouthful and a formula full. Okay, so that's our formula. Now, there's surely an easier way of doing this. Yes, there is. The calculator will do it for us. So I'll kind of walk you through what's happening. So the first thing we're going to do is on this particular table, as you look at it, there are 2 different types of data. There's first the years of experience, which I'll represent that by the letter X. And then there's the salary, which would be a Y. And down below, we have a second set. And so it's, again, years of experience and salary, which means it's just a continuation. So I'll write here X, and then I'll put CONT, meaning continued, and a Y, CONT, in parentheses, meaning it's Y and continued. So how will we do this with our calculator? What we're going to do is come over to our data set, and I'm going to type in the years of experience in as X. So we have 0.5, 0.5, 1.0, 1.0, 1.0, 1.5, 1.5, 2.0, 2.0, 2.0, another 2.0. So it looks like 4 of those, 3.0, 4.0. By the way, you don't have to type in those 0.0s if you don't want to, but the 0.5s you would. And we'll find out in a second if I made a mistake or if I got these in correctly when I type in the y value. So it should match the same length here. So let's do the y values now. 52,000. I'm not going to type in the comma. 62,000, 57,000, 61,000, 60,000, 55,000, 64,000, another 64,000. So these values are adding up here. Oops, 70,000, 66, 74, 74, 80, 75, oops, 75, 85, almost done, 89, and 90. Okay, so here's my data here, and if I wanted to zoom fit this, I'll go ahead and click that plus right there, and you see the data, it's being connected by a straight line. If you don't want it to be connected that way, you can like edit it, and so I could do it, let me turn it back on first. I could take away the lines in between by taking that, and you can just see the data that way. And so I'm going to do that this problem because that's more what I want to see is the scatter plot. So there's my scatter plot. Now it says here, a research company conducts a study to determine whether there is a linear relationship between the years of management experience and the annual salary. So we want to see, is this seem like a linear, is there a correlation going on here? And the table below shows 20 surveyed managers. Make a scatter plot. So that's what I just did here. And identify the relationship. Well, here's what I can tell you. There is a positive correlation here, or positive relationship, meaning that it is related. The more experience you have, the more you tend to work. As we go, this is X. Remember, X was years of experience. As you go right along the X years of experience, your salary seems to increase. That's the Y-axis, the salary. So there is a relationship, and I would call it positive because as you go right, you also go up. It would be negative if you went right, it went down. But this one happens to go. So I would say that there is a positive relationship. There is a positive relationship between the years of experience and salary. Whoops, so I can interpret it another way as well. I can say the more years you work, you can expect your salary to increase. So there's the relationship. It's a positive relationship. It says then calculate and interpret the correlation coefficient. So how do you do that? Well, if you scroll all the way down here to the bottom and you go to regression models, you will see that in here we have the values that we need. Okay, so it says calculate and interpret the correlation coefficient. That's the R value. So in this particular problem, the R value, according to the calculator, R equals, it's that 0.9155. Now, if you were wondering, how do I get that? Well, that's basically, if you wanted to get that, you could go and type in this, substitute all the information here to find out that value. I think I might actually have it in this Desmos. Let me just really quickly check near the very bottom. Correlation coefficient. I'm not seeing it, so maybe I've moved it out of there. Oh wait, here it is. Correlation coefficient. As you can see it, I typed it in just like they said. That length of y-1, that means that's getting the number. That's getting that 20. That there's 20 samples minus 1. So that's the only thing I substituted in for n. The rest of it is just the formula that they gave us, and it plugs in all the values. And it gets that correlation coefficient. That's how it's created. So anyways, you don't have to go to that. I just wanted to show you that it's there. And that would be our correlation coefficient. Now, after seeing me do one, here's what I would like you to do. I would like you to type in their math grade and their overall grade average. You can do this as X and this is Y, and see if there is a relationship between the two. And if there is, if it's a positive or negative relationship. And I forgot to talk about this strong and moderate. So a lot of people talk about the strong and moderate. based off of how close this number is to 1. The closer it gets to 1, the stronger it is. If it was 1, it would be perfectly strong. It would be a straight line. But this one I would call a strong relationship. Let me say strong here. Strong positive relationship between, because that R is really over 0.8. If it's over 0.8, we will say it is a strong positive relationship, or I guess it won't necessarily be positive, it could be negative, but it's strong if it's greater than 0.8. And so on this one, I would say it is strong. I'll let you now try your DOL. Pause the video if you need more time. All right, example 2. It says here, there's a formula for a t-test on the correlation coefficient. It says for a t-test of the correlation between two variables, the test statistic for the P is a sample correlation coefficient R and the standardized test statistic given by this formula, where n minus 2 is the degrees of freedom. And so we'll see that as we go through here on the next problem. All right, so it says here, in example 1, you determine the correlation coefficient R for the manager experience. The salary was about 0.9155. Test the significance of this correlation coefficient at the 5% level. So basically, we're using this formula to try to come up with this T, or the significance. So that's what we're going to come up with, this t-test, to find out the significance of this. So here's what I'm going to do. I'm going to walk you through where this graph comes from, and then we'll test the significance. So we know that alpha is 0.5%, which is 0.05. So I have that. And as you can see here, we're testing this two tails. So I need to leave this as two tails. I'm going to go over here to the alpha visualizations, and we're doing a t-test. So t distribution and the degrees of freedom, according to this document here, where we just were, is you take away 2 from the samples. There was 20 samples, and so when I subtract 2, I should get 18. And you'll see this t distribution is giving the number t 2.1, which that's that value. And so the left value, the left tail, and the right tail, let me visualize this, you can see is at 2.1 and negative 2.1. So there's their two critical regions here, at 2.1 and negative 2.1. So that's where that came from. Now let's talk about, where does this 9.7 come from? Well, that is if you plug in this formula, which that's a lot to type in. So I have that for you. If you go to the regressions and models and go to your linear regression, you will see the t-test right there. It's 9.65. So you can see that's where they get the 9.7. And it is way out here to the right. Okay. So my t-test provides the value. The t-test is going to equal 9.655. And I'll do squigglies just to say that's approximately, I'm rounding that. That's what I got here by plugging in the values. Again, you would be plugging in the t equals, or the t-test, if you will. The square, the R was 0.9155 times the square root of 20 minus 2 over 1 minus 0.9155 squared. If I remember that formula correctly, I'm going to double check real quick. Yes. And these values, that comes from that's the t-score values with 18, which is 18 degrees of freedom, is where those came from. For this providing a 0.025%, or I shouldn't say percent, let me change that to 2.5%, and this being 2.5%. That's the t values, and so that's where all that came from. Okay, now I will let you try this one to determine what you get here for your t value and if it's significant or not. Again, the significance has to do with how high that number is. And so let me go back here. And since this value is past the critical region or inside the critical region, I know this line should continue on, we would say that it is significant. This is significant at the 5% level. And I should say since the t-test is greater than 2.1, 2.1, the correlation is significant. The correlation is significant at the 5% level. Okay, so now when you go through this one, if your value falls within the critical region, it is significant. It is significant. And if it's not in the critical region, then it's not significant. Now, leading into example 3, it starts talking about how could we find out what the slope, they use the letter A, I'm going to use the letter M here, what the slope is and the y-intercept given a set of data. And so here's what the formula that happens is you take that correlation coefficient and you multiply it by the standard deviation of the y data set divided by the standard deviation of the x-intercept. So if you think about like the slope being rise over run, it's the standard deviation of the rise, the y values, divided by the standard deviation of the run, which would be the x values. Multiplied that by the correlation coefficient, you would get your slope. And the b value would be the mean, the average y value, minus the slope times the mean of the x data set. So in our particular problem, I'm now going to zoom back in on, we had that earlier. I'm going to come back up to this data set. We have all this, and I'm going to zoom in on that. So here was my data points, and we're now going to see this linear regression that we came up with. We had, let me minimize the alpha. Okay, here we go, linear regression. Here's this equation we believe is true. When I click it, you'll see there is the linear representation of this data set. There's the regression. The slope happens to be the M 2,563.58, which would refer to, well, let me come over here and I'll write it down. It says, find the equation of the regression line for the data used in example 1. Interpret the slope and y-intercept in this context. Then assess the fit of the model equation by graphing and allowing the scatter plotted data in the same window, which I've already taken part of the last one. So here's our equation, and this is the way you usually write it, is y hat. So that the y hat equals 2,563.58 x plus 57. You know what? I'm going to put commas in there to make it easier. Separate 57,953.4. Okay, so in this context, what does this mean? Here's my equation right here. What does this mean in this context? It means this, that the starting salary, that's the y-intercept, that the starting salary is approximately $57,000, $57,953.40 is what I should say. That's the starting salary. And here this says that for the slope, it's talking about for every extra year you've worked. The salary increases approximately $2,563.58 for every year of experience. Okay, so that's what this line and slope means in this context. This would be your starting salary, the y-intercept. If you have not worked at all, you have 0 years of experience, you'd be starting salary at $57,953.40. And each additional year you work, you get a raise of $2,563.58. That's what the data is indicating. Now here's your problem. Again, going off of your DOLs from number 1 and number 2, come up with your equation. Pause the video if you need more time, or if you need to go back and get your data. Here was yours for DOL number 1. You can use this data. And one more time, your DOL for this problem. Example 4. Now let's look at what's called the residual plot. So it says graph and analyze the residual plot of the salary study data in example 1 to determine whether the linear model found in example 3 is appropriate. And so what does that mean? Well, if you come over here to the regressions, you go to linear here, I'm going to click this on the residuals E1 plot, that button plot. And what happens is, and I'm going to need to zoom out here, you get this residual plot, and what's happening, and we need to ignore that, the t statistic for a moment, is what it's doing is it's showing you each individual data point. So each one of these data points here, it's showing those, and let me just change color so you can tell exactly what we're looking at. Each data point compared to the regression line. So here's your regression line. We're going to take a look at each data point compared to the regression line. And so the ones below mean that this particular individual or data point was making below what the graph or our line, our regression model would predict. Each one above would be representing someone who made more than what the line would have predicted. And so what you would want, if it was a perfectly accurate, every single point would be on the x-axis here, but because they're scattered pretty evenly as you look at it, this represents that it's a very appropriate model. Model is appropriate since your residual plot is very, I'm going to use the term symmetrical here. And maybe I shouldn't say very, but I'll just say since it's symmetrical. And so really what you're looking at is this portion of the graph right in here. Let me get some, that's what we're looking at and saying, because these are pretty symmetrical, this model would be appropriate. Now let's check your DOL. Again, you're using the same data from the previous examples. And so you're going to look at, are they randomly scattered or do they not appear to be randomly scattered nor centered? All right, example 5, it says, suppose another manager was surveyed for the salary study from example 1. The data from this manager is in the table. Make a new scatter plot of the salary data that includes the additional point. So we need to add a point here. We're going to say they have 20 years of experience and they make $85,000. And so once I do that, all my data shifted around. I don't know if you noticed that. So we've made the new data, or scatter point, and so here it is, right there. Let me take a picture of this to add to our graph. So here's my new snapshot of data. These pictures are always so large. There we go. And part B, it says calculate the correlation coefficient and the least squares regression line. So my correlation coefficient, that's the R. And so my correlation coefficient, let's just see here, the new R is approximately, where is it? 0.8582. And you can see this is not as accurate as it was before. There's the correlation coefficient and the least squares regression line. That is this equation here. So we usually write it as y hat would equal the slope now is 1,889.64 x plus the y-intercept is $60,057.20. So because this all got off is because we had an outlier. What the outlier is, you can see this is way off the line of what we're expecting to get. And so what effect does this outlier have on the strength of correlation? And the correlation strength was weakened. So here the correlation strength is weakened. Now, I would still say it's a strong weekend. I forgot the end there. I would still say it's a strong relationship because it's greater than 0.8. So the textbook actually goes like 0.7, but I kind of go off of 0.8 being strong. And so it is weaker. It is still strong, but it's weaker. All right. And what does it now mean in terms of real world is that each year you work, you'd make less, but you would start with more according to this data. Okay. So here's part C. It says, plot both the regression lines in the same window. So we want to compare them to and state whether or not that outlier is influential. So we've seen one. Let me go ahead and grab the previous picture that we had. So I'm going to grab this. And now we're going to compare this with the same picture, but without that last point. So let me just take this one point off. And we're going to look at the data here. And we'll compare the two. So let me pause this to get everything lined up right. Okay, so here are the two pictures. And if you want to determine whether or not you think this was influential, you could take a look and compare. So this one has the outlier, this one does not. I would say it's very influential because you can see as far as salary goes, starting at 57,000 versus 60, I would say it's influential. And not just that, but the rate at which your salary increases as opposed to over here, I would say it's very significant. I would rather start with a lower salary, or actually I would actually start to here, work a year or two, and then try to get on with this company. But I would say it's very significant because you can start seeing that after, let's say 10 years of service over here, you're making approximately $84,000. But over here, if you work 10 years, you're not even making 80 yet. You're about 79,000 or something. That's a big difference, $5,000. So, and that would only increase as time goes on. So I would say it is influential. I would say it's influential. Outlier is influential. Personally, I would say it's influential because of that. So that's my reasoning. And so here is your term for DOL number 5. Example 6, it says salary study. The regression line that we got from example 1 was this equation here. Use this equation to predict the expected salary for a manager with 6.5 years of service and state whether this prediction is reasonable. Okay, so how could we do that? Well, using our equation, first you can just plug 6.5 in right there for X. But what I'm going to do here is just show you, I'll just get a new equation line here, how you could type in this value. And I believe, let me check this before I speak too soon, if we say Y1, because that says Y1 there, and you plug in 6.5, let's see if that, nope, that does not work. Okay, so that does not work. What I could do is use this M though right there and say M times the 6.5 plus B, that's what they have here, B, would give me my exact value, that 6.5 years of service could expect a salary of $74,616, $74,616, I should say, and 69 cents. Okay, so now it says, state whether this prediction is reasonable. Now, how can we figure out if it's reasonable? Well, if I plot it on there, we ought to be able to tell real quick if it's reasonable. So let's put on 6.5 and 74,16.69. And so I'm going to look for that value at 6.5. So here's 6. So I'm going off this 5, 6, that's 7. So we're going to look for the one value that's in between these two gray lines. And you can see this is very reasonable. That is a very reasonable prediction. Very reasonable prediction. And if you were like, is there another way of evaluating that? Yeah, if you go to the residual plot, here at 6.5, it's this value. You can see how close it is to the line. It's only $935 off of the exact the line that we had earlier. So I would say it's a very reasonable prediction. Okay, in part B, so it says use this same data. I'm gonna go ahead and delete the 6.5 so it doesn't mess with my numbers here. Okay, we now want to know what's the expected salary for a manager working 40 years of experience. So if I looked at 40 years of experience, so I'm gonna put that in there. So M, I already got the slope, 40 years of experience. Should generate a salary of, it says $160,496.73. Now that's a great salary. I would love to make that salary. I don't, but it would be fantastic if I did. I'm going to try this. Let me come back here and zoom in this data properly. So if I wanted to say, well, does that seem like it's increasing at the right amount? Well, here is 40 and 160,496.73. If you check that value out compared to the residual, you'll see that that is right along on the prediction. That's, I would say it's very reasonable. People do make that amount of money. If they've been working as a manager for that long, people do make that money. So again, I'm going to say that's a very reasonable prediction. It doesn't seem like it's too far off of where the data is heading. So it seems very reasonable again. Now, someone might say, what is something that's unreasonable? Well, let's say it was a negative relationship and you put in 40 and it ended up with a negative salary. That would be unreasonable. So here, I would say it's very reasonable as well, just because it's going in the right manner. Okay, use your same data and come up with whether or not you think the data from example 3, that is, if it's reasonable or not, and what your value would be, what your result would be. Pause the video if you need more time.